And I think we're live. 2 o'clock came really fast around here. I wasn't expecting it, but I am ready. Let me turn off this fan here. Oh, welcome to another edition of RockSim Live. This is where we talk about RockSim and all the cool things that you can do with it, simulating model rockets. I am Tim Van Milligan. I am your host. I have a little bit of a cold, so my voice is a little bit scratchy, but I'm doing okay. I'm doing fine. I hope everybody is doing well. COVID is like running rampant through the country right now. We did have some staff out here at Apogee for the first time in this whole 2-year pandemic. But I'm sure it's, one of them is already back. So we're doing fine. And things are progressing as normal, so if you need a rocket, we're still shipping. Yeah, so we got some people in the house today. We have Carlos from Marietta, Georgia, Mark from Orlando, Johans from the Netherlands, Kevin's Models and More. Let's see if there's any questions so far. Wow, level 3, most powerful thing I launched so far was a D12 cluster, says Johan. My rocket friend terminated the broadcast. Somebody terminated the broadcast last time because the sound was so bad. I switched the battery in my microphone, so hopefully that was the problem. Carlos says, does RockSim or the website show the drag different shape nose? Show the drag of different shape nose, chosen nose cones, or is it just based on diameter, speed, or something else? Okay, that's a good question. We can get into that one. Kevin's Models and More says he's from Las Vegas. So cool. So if you're not watching live, and if you're new to this, this is where we talk about RockSim and the software. Let me switch screens here so you can see my screen. RockSim comes from Apogee Components, and if you're on the Apogee website, which is apogeerockets.com, you can find more information and the previous episodes of the RockSim Live training by just clicking on this image right here. And that will take you to our previous episodes. We are on episode number 52 today, because I can see the episode 51 from the last time, last Friday. If you're wanting to buy RockSim, you would go to Shop, and then come down here to Rocket Software, click on Rocket Software, and then you can buy it right there. If you just want to go information on what it does and maybe download a trial version, instead of hitting the shop menu, go to How To and Guides, click on that, then come here to Software, click on that, and then you can download the free trial right here, or you can see the what is RockSim. This is kind of like the basic overview of what it is and what it does. And then over here on this side, there's more tutorials, there's videos here. Again, the RockSim Live training, which goes to that page that I just showed you. Yeah, this is kind of like where you start for information. So let's go into RockSim, because Carlos had a question about drag. So I have RockSim open. This is what RockSim looks like. Let me open up a new design, something a little bit simpler. So to do that, go here to the File button, File Open, click on that. Come on, there we go. And it's going to go into your database, and right now my database is pointing at a different file than yours might be. Let's see if I can find one that I like. Let's sort them. The Apogee Habu. This is a rocket that's going to be coming soon. It's a product we're still working on, and this is what it looks like. It's kind of similar to an Estes Alpha in shape, except it's a little bit bigger. So it's, if you look at this rocket right here, this is a 1.3 inch diameter tube, and that's what the Habu is. It's a little bit bigger, short and stubby, and it's got an ogive nose cone. So what Carlos is asking is, how does the drag change with changing nose cones? Let me quit some of this stuff here because it's kind of popping up. Get back to RockSim. There's RockSim. Okay, so if you're in RockSim and you want to know the coefficient of drag, you go up here to RockSim menu at the very top, come down here to CD analysis. That's coefficient of drag analysis. Click on that, and that brings you this screen. So, and drag is a function of the velocity of the rocket. So on this chart right here, it gives you the total drag coefficient is the red one, is the red line. And right now I'm at 0 miles per hour. So at 0 miles per hour, the coefficient of drag is 0. There's nothing acting on the rocket. But as soon as the velocity picks up, like right now I'm at 430 miles an hour. Now we have drag, and our drag is estimated at 0.325. And of that drag, the nose and the body is equal to 0.1335, or it's about 41% of the drag. Okay, so now this rocket has an ogive nose cone. So let me change this to go to a typical rocket speed, call it like 200 miles an hour. So at 200 miles an hour is 0.347, and then it's 0.1534, or 44% of the drag. So the lower the speed, that nose cone and body is creating more of the drag. So let's change the shape of the nose cone and see what that number does. So to do that, we need to see the parts of the rocket, and for that you need to go to the Design Components tab right here. Click on that, and here's the nose cone, and we're going to edit that nose cone, and what we're going to do is change the shape of the nose cone. And to do that, we'll go here to we can choose any one of these shapes. I'll just choose an elliptical. Okay, and you see that just by doing that, the nose cone shape changed a little bit. I'll go back to that so you can see that again. So before it was ogive. See, it's nice and pointy. And then if we change it to, come on, elliptical, it's more rounded at the front. Okay, so now let's click OK. And let's go back to the coefficient of drag under the rocket menu and see what it did. And we were at, what did we say, 200 miles an hour? So I'm typing in 200 miles an hour at the bottom, hitting the tab. And now our drag went to 0.161 for the nose and the body tube. So an elliptical nose cone has more drag in RockSim than the ogive nose cone. So now I'm going to answer your question, and you're not going to like the answer, but this is the way RockSim calculates it. The way RockSim calculates coefficient of drag of the nose cone is based on the wetted surface area. So what does the wetted surface area mean? It means if you took the nose cone of the rocket like this and you just dipped it into paint, that is the wetted surface area. So if the more paint on the rocket, the higher the drag is going to be. So to get a lower drag coefficient in RockSim, what you have to do is have a less surface area. And so the less surface area, there's two ways to do it. One is to shorten the nose cone. Just by shortening the nose cone, we can probably make this number go down. Let's go up here to nose cone. And let's shorten the length. Let's call it 2 inches. And see, now it's nice and even stubbier. And click OK. And go to the rocket drag again. And let's make this 200 miles an hour. Hit tab. Oh, it did go down, and now it's down to 0.139. I think before it was 0.16. So just by shortening the nose cone, you're creating less surface area, so you're going to have less drag. As far as shapes go, what shape has the lowest surface area? This is a question you can answer. So if I go here to the nose cone again, and if I choose the right shape on here, which of these has the lowest surface area? Does anybody want to give an answer? While I'm putting the nose cone back on the rocket, I have to push all the shock cord back in. Nobody's answering. Well, the answer is the conical shape. So if I change nothing else, and if I make it conical, let's see, now it's pointy. And if I go to the CD analysis again, go to 200 miles an hour just to do an apples to apples comparison, we're still, before it was 41%, now we're down to 40%, just by changing the shape to a conical nose cone. So now your question is, and this is why I said you're not going to like it, is what nose cone shape in real life, not in RockSim, in real life, what nose cone shape has the lowest coefficient of drag? And for that, we have an R&D report on the Apogee website. I'll show you how to find it. Okay, so you click on How To and Guides, come down here to Educational Resources. Nope, not How To and Technical Info, right there. Click on that one, and then come here to R&D projects from the NAR. Actually, this is in 2 spots. One is in this section, and one is in the newsletter, because I actually put it in the newsletters as well. So maybe an easier way to find it is to go to Peak of Flight newsletter, go to all newsletters. Okay, and then on this page that lists over 564 newsletters, do a find on this page. And remember, to do a find on a specific web page, do Control F on your keyboard. On the Mac, it's Command F. And then it brings up a search bar up here. And it's only going to search on this page for a specific word. So I'm going to type in nose cone. And I got 23 matches, so I need to find which one it is. So I'm just going to go through them. And I'm looking at the topics as I'm clicking through them. Okay, there it is. Drag of nose cones, issue number 346. So I'm going to click on that and I'll open it up. This is an R&D report that my daughter did. And what we did in this R&D report is we took the nose cones that you can buy as part of the nose cone science fair kit. This link right here. So if you click on that link, there I go. I already went to the page. You get an Avion, and you get 1, 2, 3, 4, 5, 6 different shapes that you can test. And so what we did is we actually tested these nose cone shapes. But instead of just launching the rocket, we went and we put the nose cones in the wind tunnel at the United States Air Force Academy, which is here in Colorado Springs. They've got a state-of-the-art research laboratory there, because that's one of their missions there at the Air Force Academy, is to do research. And so we politely asked if we could test these shapes in a wind tunnel. And so that's what she did, is we built the nose cones. I think we even actually did a couple more, because we took that nose cone there. And we made them all the same surface finish, so only the shape was being tested. And there's my daughter right there. And this is the wind tunnel that we put the rockets in. And she had a helper, Katrina, that helped her put the nose cones in the tunnel. And you can see right here, she's making sure the nose cone is perfectly level so that it's not at any angle of attack. Here's another picture of the wind tunnel, more pictures of the wind tunnel, and how the nose cones were mounted in a tube in the wind tunnel. And then right here, this bar is a force balance. And so as the wind was blowing over the nose cone, it would hit on the nose cone and it would measure the force that was created just by the air flowing over the nose cone. And this one looks like a short conical nose cone. And this one right here is a body tube where the nose cone's removed. So you got just trying to force air into a tube that's plugged on one end. And there's me in the background. And this is where she's writing down the data, and my other daughter, Allison, helped her. So you want to see where the data is. Okay, so here's the data. So what we did, let's see, did she, okay, so this page, let me zoom out a little bit so you can see more of it. Okay, so she, so the best shaped nose cone in real life was this one here, the elliptical nose cone. The elliptical nose cone in real life at speeds that we were testing at, which was I think around 100 to 150 miles per hour, which is typical of a model rocket. The elliptical has the lowest drag force. The parabolic wasn't too bad either, just a little bit more. But then as the nose cone got shorter and shorter, which is opposite of what RockSim is, the drag got higher. So the short conical nose cone, which we just showed in RockSim, where RockSim has the lowest drag, the short conical, actually, the drag is starting to come up. And if it's a plugged cylinder, it's really high. And if it's a cupped cylinder, like, trying to ram air into a body tube, that's really high. That was 10.45 grams of force. And if you vented that, it only went down a little bit. So what we're saying is RockSim, as far as predicting the coefficient of drag, the nose cone shape, and I'm the first to admit this, RockSim is not a coefficient of drag prediction expert machine. It's not. What it's really good at, and what I use it for, is trajectories, figuring out the trajectory of the rocket and and how high it's going to go. But to figure out how high it's going to go, you need a good coefficient of drag. So that's why RockSim always has a mass or a coefficient of drag override, so you can override the prediction that RockSim gives you. So it's going to get you in the ballpark, but it's not going to be super duper accurate. So that's why I say, Carlos, you're not going to like the answer, because it's not going to predict a really good coefficient of drag for you. For that, you need to go do wind tunnel testing, or actually fly the rocket, measure the altitude, and back out the coefficient of drag. And we've talked about that a number of times here on how to do that. And if you want to know how to do that, put it in the chat and I'll bring it up again. Otherwise, go to the Apogee website, and again, go to the RockSim Live topics, and that was under software, RockSim Live training. And in here, you can do a find on this web page. Again, it's Command F on the Mac, Control F on the Windows. It brings you up a search bar, and you can type in like drag. And you know, we've talked about it 7 times, and here it is, episode number 39. How to determine the coefficient of drag. And if you go to that YouTube video right there and you scrub to 12 minutes and 30 seconds into the video, you'll find where we talked about how to figure out an actual coefficient of drag for your rocket. So hopefully that answers your question. And let's see if we got any more questions coming in over here. And I'm going to take a sip of water because my voice is getting really, really scratchy. Question repeat for attempting surface level 3. Mark Gillette says he's attempting my level 3 certification tomorrow. Any words of wisdom you can share? Yes. Mark, use the launch visualizer. So what's the launch visualizer, you ask? The launch visualizer is an online website where you can test your rockets, and there's no software to download. So if you're watching this on YouTube, you can go there right now. It's just at rocksim.com, and you can test fly your rockets. And let me see, I'm going to need a level 3 rocket for Mark. So let me see if I can find my level 3 rocket, or at least something that's big. Let's type in my search bar level 3. And I'm searching through here to see if I can find a RockSim file. That's a level 3 RockSim file. Something big. Come on, I want to search by name. Let's go to my RockSim designs. I just need something big. There we go. Here's a level 2. We'll use that one. Okay, so in the launch visualizer, I just needed to know where to find it, because I'm going to upload a new design to into the cloud. And so I'm going to pull it off of my computer and upload it into the cloud somewhere. And so when I click on browse, this is going to browse my computer. Okay, RockSim Designs, and that was Tim level 2. Tim level 2 rocket. So I'm going to upload that. And say upload, and it's going to upload it. Okay, and click OK, and then it should show an image of the rocket right here. Okay, we got a high power pad, and this is the level 2 kit. And you can see this is a 3D image, and I can rotate it around. I'm doing a right click and then just dragging. Left, right will rotate, and to pan up and down is right click and hold. If you're seeing black, you're looking from underneath the ground. You can see the wind direction here where I'm launching. It's coming out of the west. So my recommendation is to run simulations and see what happens. So we need to pick a launch site. If you know where you're launching from, let me know, and we can try to run a simulation from where you're launching from. I'm looking for that comment. Mark Gillette. And he's from Orlando. So he's flying from somewhere near Orlando. So when I'm going to my launch sites, I'm going to choose a launch site. And I'm going to try to find a launch site that's close to Orlando. So I'm going to type in Florida. We have the Florida Space Modeling Association. I'm going to open that one, and it's going to show me a map of that launch site. This is in West Palm Beach. So I don't know if he's launching from there or not. It doesn't look like a really, really huge launch site. So for a level 3, he's probably going to have to keep it low. So this is why I would run simulations, because you want to see what's around you and what obstacles you might face trying to retrieve your rocket. So let's assume that the launch pad, let's zoom in a little bit. Let's say there's a nice road right here and people might park along there. So let's say that the launch pad is going to be right here. And I'll confirm the launch site by hitting the button down here on the bottom. And what it does is it plugs in all these numbers right here, so you don't have to do anything. And now I'm going to zoom out again. I want to get a feel for the launch site. We got a lot of houses to the east. So north is straight up. We got a lot of houses to the east. We want to avoid those. We got a lot of open space over here to the west. And it looks like it's kind of marshy and swampy down here. So I'm gonna launch to the west, and I need to know that. That's what I'm putting in my mind right now, because now I'm gonna go configure the launch site. Okay, so here's the rocket sitting on the pad, and right now it is angled a little bit to the west, a little bit west-southwest, so I'm going to angle it more to the west. So now it's angled to the west. I'm looking at that, and that's okay. The wind, I'm going to say right now we got a wind coming out of the west at 270 degrees, or 8 miles an hour. So again, piece of information you want to put inside your noggin. Now we're going to select a rocket motor, and I'm going to choose engine. And this part is a lot like RockSim, where you're going to choose the engine. And I want the biggest engine I can find. Actually, I should probably sort by engine code. Okay, so the biggest one in RockSim right now, I got a K1127, 38 millimeters. I don't think that's actually possible. But, you know, it says unknown. So I don't know who owns that one. LB and LR. You know, I will go with the Aerotech J25. Okay, so now we need to select our delay. And at this point, we don't know what the delay is going to be. Since it's a level 2 rocket or a level 3 rocket, there's a high probability, particularly on level 3, that you're going to have dual deployment. And with dual deployment, you're going to have 2 parachutes. One's going to come out at apogee, and the other one's going to come out at some altitude. So for right now, I'm going to leave this as plugged. Plugged means there's no ejection delay that's going to push the parachute out. What we want to do is set our flight events that's going to control when the parachutes are going to come out. So I'm going to click OK for now. So now the motor is loaded. So the motor is here, an Aerotech 825R. R stands for red line, so it's going to have a nice red flame. And we don't have ejection delay. It's set at 0, so we want to set that as plugged. Okay, I just want to make sure that's plugged. And now we're going to go to the flight events. And this one only has a single parachute in this file, so I can only do single deploy. So what I'm going to do is I'm going to deploy this one at, let's do an altitude. For right now, let's call it Apogee. This is going to be the worst case situation. This is going to be, it's going to drift really far. And so once we have the parachute and we're ready to launch, and the launch button is behind my face here. It's down here. And if you're on a phone or a tablet, what it does, I can kind of simulate this. This is how RockSim would look on a phone or a tablet. And then it puts all the buttons, instead of being down the side, they're across the top. And the launch button is right here. But sometimes the launch button is covered up. So you always got to go all the way to the top if you're on a phone or a tablet to find the launch button. But since we're on a desktop, I'm going to make my screen big. There's no reason for you not to see a big screen. Okay, and then here's the launch button, and I'll just choose launch. And it's going to use 929 credits. Each credit is equal to 1 Newton seconds of power, so it depends on what motor you're using. And we'll just go simulate. And this is going to take a second, and it's running it on our servers in the cloud. And now that's done, so now it's loading the maps. Okay, so now here's the rocket sitting on the pad. I'm going to zoom out, kind of get a lay of the land. Okay, so there's the road where all the cars are going to park. And let me orient the map around so north is at the top. Okay, so north is up in the distance. The rocket is right there on the pad, and you can see this weather cocking cone. And that kind of gives us an indication of how high the rocket's going to go, because if you zoom out, you can see, once you see the top of the cone, that kind of gives you an indication on how high it's actually going to go above the ground. So I'm trying to make the cone as big as I can, trying to move the launch point down here towards the bottom just by clicking and dragging on the screen. Down here in the mini view, we see the rocket sitting on the pad. And at this point, we're going to launch it. I can already tell it's going to be 2 minutes in the air, 120 seconds. And if we run the simulation, the rocket's taking off. You can see there's fire coming out, and you can see the trajectory of the rocket going up here. Each of these dots is 1 second into the flight, so you can kind of get a perspective on time. It's running in real time right now. We're getting, I'd say, close to the apogee point, because now the rocket, yeah, so we hit apogee, and now the parachute deployed, and now it's coming back down to the ground. And we're at an altitude of over 2,500 feet right now, which you can see from here, and it's coming down. And the distance, it went upwind about 1,000 feet, more or less. And it's coming down, and it's coming down pretty good, nice and fast, actually, I think, because the slope of this line right here, where all the points are, is pretty straight. Now I'm going to speed this up because I don't want to wait 2 minutes. I'm just going to click and drag and put that over here at the end. And it's going to take a second for the computer to catch up to what I wanted it to do. Okay, so now it is back down on the ground, and it looks like we stayed on the field, which was pretty good, but I don't know what size parachute was in this rocket. But that, look how close to the pad that thing landed. Only 127 feet. Right down here. See, the launch pad was right here, and it landed right here. That's like as good as you're going to get in real life. And so this, you can rotate around and see what that trajectory looked like. I'll zoom out a little bit. Now we're looking straight to the west, and now we're looking more towards the south. So that would be the first thing I would do, Mark, is just to test, make sure your rocket's going to stay on the field, dial in your delay. So now if we click here, it'll take us back to the summary screen. And then from the summary screen, we can see what the optimal delay was. So if I was setting the delay with a delay setting tool, I would dial it in at 11.21 seconds. So it reached a maximum altitude of 843 meters. It's interesting that this says feet over here and this says meters here. They should be the same. Let's change them both to feet. Okay, so that was 2767 feet. I want to just check this because that seems like a little bit of a bug, because they should both be whatever the user sets. Yeah, it didn't change that. Okay, I get to notify the programmers about that. Yeah, so now what size parachute was in there? That's a good question. And to do that, to figure that out, I have to open up that design in RockSim to actually see what it is. So that was in my design folder. And I'll scroll down to that design. Click open. Save the changes to that one, say no. Okay, so here is the parachute. So this is the parachute right there. And if I open that parachute up, it tells me that was a 60-inch parachute. That's not bad. 60 feet, that's 5 feet in diameter. So that's a good sized parachute. So I would be happy with that. So you could actually, instead of using dual deploy, you could actually use single deploy if you wanted to on that flight in those conditions on that field. All right. So let me take a drink of water and take a look at these comments and questions. People did answer the question about which shape nose cone has the lowest drag in RockSim, and people were guessing conical, and they were right. And Carlos said, would a pin win? Having a nose cone the size of a pin, and the answer is yes, that would win. Michael O'Brien from Mesa, Arizona is here. Mark Gillette says launching from Tampa, Plant City, Florida. Okay. Now you got me curious. Where is Plant City, Florida? So, Plant City. So, choose a launch site. Let's see if that one's in here. It's not under the word plant. I'm trying to type in Tampa. Tripoli, Tampa. Okay. New launch site. It's coming up. It's still loading the maps. I'm kind of getting the lay of the land here. So here is Tampa, Florida. And if you're from outside the United States and you want to know where Tampa, Florida is, it's on the East Coast. It's that part of the United States that sticks out in the ocean. Kennedy Space Center is over here. This is where I used to work before I joined the rocketry community. So Tampa, Florida is on the other side of the state. It's probably about a 3-hour drive from there. And let's zoom in and see what the field looks like. This is definitely not a field, because there is a lot of buildings there. So we don't have the field location correct from Tampa, Florida. So what you can do, Mark, is go in the launch visualizer, find your field. Say it's like way over here by Lake Santo Tosa, whatever that you want to say that is, and say this is the launch site. See this nice field here, and just put a pin there by double clicking. And so that's the launch site. So put it in the exact location of the launch site and confirm launch site, and that will redo all the numbers over here. See all those numbers changed. And then do right here, save this launch site, and you'll call this Tampa site. And you give your club name, the club URL, so we get that right. And if this contact email, nobody sees that. Well, yes. If you want your contact email to show, put that down here in description or special notes, and so that I see it. If you don't want it to be seen, say don't show email. That's totally fine. I don't want to expose anybody's email. A description of the website, any kind of special notes, is permission to launch there required, and then hit submit. And what this does is it saves it into your own database. This is still private. Nobody has seen it. So now to share that with the rest of the world, so that the rest of the world can find your launch site, and so this is how you can advertise your launch site and get people to come visit you, to make your club grow. We all want our clubs to grow. Makes a club stronger. When you got more members, there's more dues. When there's more dues, you get better equipment. And so you want your club to grow. So to make it grow, click on share this launch site. And when you do that, it's going to bring up a list of all the ones that you've created in your own database. And so here's my Tampa site that I just created. And you click on that, make it public, and then hit share. And what it does, it's not shared immediately. I get an email to me personally so that I can check out the website and check out the launch site here in the launch visualizer, make sure it looks legitimate, because I don't want to share somebody sharing something that's not a legitimate site, like launching from the top of the Empire State Building in New York City, or from the pinpoint on the pyramids in Egypt. It's kind of not legitimate, but you could launch there. But when the purpose of me making them public is to help clubs grow. I want to support clubs, and I want to get your new members into your club. So that's why I want to make them public, and that's the only reason we make them public. So Mark, do that for me. Send it to me the way I just showed you, and then I'll make it public. And so that way, the next time we do one of these things, we can actually show where the actual club launch site is. Because I don't know, the list that we have was taken from the NAR website and the Tripoli website, and they just have like a city, like Tripoli, Tampa, Florida, and that's not it could be a building. So if you were launching from that launch site, again, it looks pretty good that you could launch to the west. So we're just going to rerun the whole simulation one more time. I'll just click over here, launch, simulate, and it's going to run it. But this time it's going to show up on our new launch site instead of that one there that was in West Palm Beach. Okay, so it's loading the maps again. And I'm going to orient it around so that north is towards the top. Okay, and then we'll launch. You can see the rocket taking off. I have the smoke turned off. Let's see the rocket. We discovered an issue the other day is when you have smoke turned on, each particle of smoke is an actual physical object. And so the more physical objects you have in the launch visualizer, it kind of slows things down. So if you want things to run a little bit faster, just turn off the smoke. So how do you turn off the smoke? I'll show you here in just a second. So here's the rocket coming down, and you can see in the background it's going past the lake. I'm kind of looking towards the southwest right now. Maybe zoom out. See, it's under parachute right now. And this, you know, there's that launch site right there. It's not oriented to the north, so I'm going to reorient it. Yeah, I probably went a little too far. You can see north. And the rocket's coming down, and it's probably going to land pretty close again. You know, there's probably not much difference between West Palm Beach and Tampa, Florida. They're both in Florida. Florida is relatively flat. Trying to get the scroll bar to scroll. When you get a long flight, there's more math that it has to do. Okay, let's see if it'll go over there to the end. Doesn't want to go. I got a lot going on my computer right now. I got the launch visualizer going. I got the live stream going. I got other software running in the background. You can see that this one, you know, again landed about 128 feet away. Same weather conditions, so it's typical that you would expect. So now if we launch this same rocket in Colorado, where we're at a higher altitude, we would definitely get a different trajectory. Let's see what else is going on over here. MOB Rocket says, attempting my level 1 cert tomorrow in Tucson, Arizona with Southern Arizona Rocketry Association, flying the Apogee Zephyr. Everything I learned about preparing for this, I learned from Apogee videos and reports. Cool. Johan says, I recently saw an old video from you, Tim, on certification flights. Launch straight up, Tim, to prevent chute tearing. Yeah, so that's a good point. You know, ideally, on your certification flight, you got to be careful about opening your parachute too fast. Anything, you know, my rule of thumb is anything above 50 miles an hour is too fast. So imagine you're in a car and everybody has opened the windows and put your hand out the window. And imagine you're doing that, but you have a parachute and you throw the parachute out and you're holding on to it, and the parachute is going to open as soon as it hits that gust of wind. And so what we're saying is anything above 50 miles an hour, there's probably a good chance that you're probably going to shred your parachute. So that's my threshold speed. And if you're launching at an angle like we're doing here, we're going to have a higher opening velocity because the rocket has horizontal velocity than if you went straight up. And you can get that number, again, going here to the summary screen, and we're looking for the column that says velocity at deployment. So here is the velocity at deployment, and you can see on that last flight we were at 81 miles per hour. So we were going too fast. So how can we go slower? Again, like I said, you can go more straight up. So if I go here to starting state, and instead of launching at 11 degrees, let's launch straight up and rerun the simulation. And see if we can get that opening speed at a lower velocity. It should be like really low right now. Again, we can run the simulation with the rockets taking off. And if we don't want to wait, we can just take the scrubber and go all the way to the end. But I don't care about that. All I want to see is that velocity of opening. So I'm going to close that, come here to the chart, and again, we're going to come over to velocity at deployment. And now we're at 20 miles an hour. And that makes sense because we're going straight up. Why does going straight up and we're ejecting right at apogee? If the rocket went perfectly straight up, deploying at apogee would be deploying at 0 miles per hour. So why is this number here 20.26 miles per hour? And the reason is that the rocket has some horizontal velocity at deployment. Let me zoom in here. Let's see the rocket. Oops, I gotta actually, I want to catch it right at apogee. And when it goes to apogee, I'm going to get a dot that's a different color. So right there, it's a green dot. So I'm going to pause it right there. And if we zoom in on this, you can see, if you look at the arc, so this green line that's going up, you can see that it was starting to tilt over a little bit. Let's see if I can move the rocket back in time just a bit. It will go back, but it's a little bit slow when you're doing a big simulation. The higher up you go, the more data is, so it's a little bit slower when there's a lot of data. Yeah, it does want to move. Looks like there's, down here in the ground, there's like a gravel pit or something. Okay, you can see that the rocket is not going straight up, it's at an angle a little bit. And that's because, as I said, and why is that? Why is it at an angle? Why did it arc over? It's because it's weathercocking into the wind. That's typical of a rocket. If a stable rocket will weathercock into the wind, the more stable it is, the further it's going to weathercock. And then that number is going to be higher. Yeah, there's nothing you can do about it because you got horizontal velocity and you can't cancel out your horizontal velocity like you can cancel out a vertical velocity with doing deploy at apogee. Kevin says, with the advent of universal astrocam, where is the ideal location to mount it? On the CG point or up near the nose cone? Can a rocket be too nose heavy? So basically what Kevin is asking. So let's take a smaller rocket. So we're going back into RockSim. Smaller rocket, so I'm going to open up a smaller rocket. I want something kind of maybe bigger than the Habu. Maybe it's something like an Estes Big Bertha. Let's see if I got an Estes Big Bertha in here. Estes Designs. Estes Alpha Big Bertha. Okay, open that up. Save that one, no. Okay, so here is my Big Bertha. I'm going to look at it in 2D. So now to simulate an astrocam, it's going to do two things to the rocket. One, it's going to add drag, and the other thing, it's going to add mass. So, and his question is, can a rocket be too overstable? So he's already thinking about this, which is really good. So to add a mass, so what I'm going to do to add a little bit of drag and a little bit of mass, in my parts right here, there's no thing called astrocam or camera or anything like that. We have a couple of choices. We could add it as a pod, or we can add it as something as simple as a fin. And that's what I'm going to do because that takes less time. So where do you want to put the astrocam? So I'm going to attach it to this tube right here. And so it highlights the tube, and then I'm going to go here, I'm going to add it as a fin, and I'm going to cancel out of the database. So now I'm looking at the rear view of the rocket. Let me change it to a side view or a top view, Okay, so there's our fin, but it's set at 3 fins right now, so I'm going to change it to 1 fin. So now we're down to 1 fin, and I'm going to move the location of that fin towards the front. And the other thing I'm going to do is going to change the size. So I'm just going to kind of guess at the size here of what the Astrocam is. Let's call it a root chord of 2 inches, tip chord of 2 inches, a span of, let's call it 1/2 inch. Make it like that. And I don't think it's that swept, so we'll make it like there. So that's our camera. And then I need to give it some thickness. So right now, it's we're going to call it like 0.75 inches thick. A nice big beefy fin. So if I look at it from the base view, so there's my fin right now. So now it's kind of sitting on the outside of the rocket, and it's in line with the fin. So I need to move that. So we'll go to the radial position tab, and then slide that over to the side so it's looking down between the fins. And then, oh boy, that's turned on too, so let me turn that off. Quit. So look at it in 3D. And there is my Astrocam here mounted on the side of the rocket. So now it's added weight. Let's see how much weight has it added. It's added at 1.57 grams, and I can adjust this 2 ways. Either I can change the material, or I could use a mass override. It's simple just to use a mass override. So I'm going to code here mass override. Click this button that says use this mass, and let's call it, I don't know what a camera is, let's call it 7 grams. Hit tab. It says now the mass override is on. Even though it's calculating this, it's going to ignore this calculation and use 7 grams. But now how do you, when I add it as a fin, it's going to add a little bit of drag because fins have drag. It's not going to be a lot of drag. And as we said at the beginning of this episode, RockSim is not the best at giving you accurate drag prediction. It's going to get you in the ballpark, but if you want to be accurate, you actually got to go out and measure it. So I'm just going to use what the drag coefficient that RockSim estimates right now and click OK. And then I want to, oh, this is a booster. Let me remove that booster stage so it doesn't think it's crazy here. See, it says 2 stages. I'm going to change that to a single stage. Okay. And the booster, now if I go back to the components, the booster stage is now gone. We only have the sustainer. Now we can, so now we have the rocket where the Astrocam is at the front, and so what's it going to do to the flight? And so you were correct when saying you could make the rocket too much overstable, but how stable is, or how much overstable is too much overstable? And we built this into RockSim as a way to tell how much is too much. And it's called the weather cocking cone. So if I prepare for launch and I choose an engine, let's choose an Estes C6, and we'll choose a 3-second delay, click OK. It's going to deploy it at 3 seconds. The simulation, we leave most of that alone. Starting state, I just want to see where it's launched from, so we're going to go straight up, 0-degree launch angle, and this is at 700 feet, and we have no wind. Let's give it some wind. I like using 8 miles an hour as my test wind condition, because that's kind of like typical. You know, whenever you go out, there's always a little bit of wind. 8 miles an hour is kind of breezy. It's not like really strong. You know, the NAR safety code says 20 miles is it. After 20 miles, you can't launch anymore. So 8 miles an hour is kind of breezy. So we expect this rocket to weathercock. So to see the weathercocking cone, come here to the flight profile, click on that, and it's going to run the simulation. And the weathercocking cone is this right here. And we kind of showed that the launch visualizer also has it. And what we want, the criteria we want to decide if the rocket is weathercocking too much is the apogee point, is the highest point of the flight inside of that cone. Eventually the rocket could arc outside of the cone, but is the apogee point inside the cone? Because what this does is it kind of tells us that the rocket is going mostly up, which is the safest way. We don't want it to go too far into the wind. And so our safety criteria is that cone. So when we launch that rocket, does the apogee point stay within the cone? So you can click on it and launch it, and you can see it's arcing over. It's getting close to apogee. Okay, so yes, we are inside the cone on this flight, which is good. Can we change the conditions to make it where it's outside the cone? And that's easy to do, so we'll just go back to prepare for launch. And I'm going to just change my starting state to, I'm going to angle the rocket, let's call it 7 degrees. That's hardly nothing. You know, that's it. And let's see it again. Okay, so here again is the rocket. Notice that before, when we launched it, the rocket was sitting over here. So RockSim had to, it kind of thinks that it's going to go further arcing over, so it's leaving room for it to go further over. Now let's see when it launches. Okay, so now we're outside the cone. And yes, so at this point, we're calling it too much weathercocking. And so you can change that by changing the launch angle. So that's one technique that you can use. Another technique that you can use is use a higher thrust rocket motor. So here we have the C63. Let's change that to something with a higher thrust. And to do that, the easiest way to do is to look at the number right after the letter. So C5 is a smaller number, so that's lower thrust. C3.4, that's even lower thrust. C2, even lower. C18, that's higher than a 6. So if we choose a Quest C18, and let's make it a really long delay, and click OK. So now instead of the C6, when we launch it, it's going to be launched with a C18 from Quest. And remember that time, the first time it went outside the cone, and it was pretty far out. So now with a C18, where is that going to be? And so when we launch it, see now it's staying inside the cone. We didn't change the launch angle at all. All we did was change the motor. Here's our apogee point right there. So just by changing the motor, having a high thrust motor, we can stay within the cone. And that's a really good technique. And why is that? Is because the rocket is going so fast. Higher thrust means it's a bigger kick in the butt. It's just kicking that rocket off the launch pad really fast. And so you got wind coming from one direction, and you got speed going the other, and the speed wins because it's going faster. So you have less weathercocking into the wind with a higher thrust rocket motor. So that's a good technique as well. And then, as you mentioned in your question, you can also move the location of the camera, putting it closer to the center of gravity. Right now, where we have it located, here's our center of gravity. We have the mass way up there. So if we move that fin, so here's the fin, and let's call it the camera so we don't get confused. And let me see it in 2D. Okay, so you can see it on my screen right here. So here's the fin, and I'm going to change the location by grabbing the slider bar here. And watch the location of the center of gravity as I change this location. You see, and it's shifting backwards. So now rerun the simulation with the new center of gravity location and see what the trajectory looks like. So to answer your question, the answer is buried in RockSim on where to put the location of the camera. We want to put it at a location that maximizes the view of the camera and also optimizes the trajectory so we get a safe flight, because safety is the most important thing. The better view on a camera, typically it would be at the bottom of the rocket, right between the fins, because now you don't have any fins obscuring the lens view. But being that close to the rocket engine, you might get some soot swirling around. If it swirls around far enough, it could get on the lens and kind of fog your lens. It'll rinse right off, of course, but during the flight, it might be there. And I've never tried this, so I don't know if you're going to fog up your lens or not. But that would probably give you the best view. But by putting it back there, now the rocket is becoming less stable. As long as it doesn't become unstable, you're going to be okay. So here it says I'm overstable. If that switches from overstable to stable to unstable, now we have a problem. Now we definitely want to move it forward. Move that, because that's going to move that center of gravity forward away from the center of pressure, and that makes the rocket more stable. Ooh, okay. Johan says, the delay set in the model file makes not deploy at Apogee. I'm not sure what he's talking about. Will RockSim warn, says Carlos, high velocity fins snap off due to poor ejection choice or poor engine choice? So basically what we were talking about with a C engine, you want to really kick the rocket really fast. So it is possible to kick the rocket so fast that the drag on the fins becomes so large that the force of drag is greater than the stiffening force of the glue joint, and you could snap a fin off going really fast. And this is called exceeding the speed of balsa. And shreds happen, the faster the rocket goes, the more likely you are to shred. Anything going supersonic, greater than the speed of sound, high likelihood or higher likelihood of fins coming off. And so you really want to make sure your fins are on really strong. Does RockSim calculate that speed? And the answer is, unfortunately, no. RockSim is not a structural analysis program. And in reality, we couldn't actually do that anyway, because we don't know what techniques you use to build your rocket. Because the way you mount your fins is going to make a difference in how strong they are. And I don't know how you've mounted your fins. Are you just doing a surface mount, a butt joint like this, where you're just butting up against the tube? That's the weakest way. Are you doing through the wall fins? That's stronger. Are you putting on internal fillets and external fillets, and how much strength does that add? And that's going to depend on how big the fillets are. And you can see there's a lot of variables here, and we just don't know them. So that's why RockSim is not a structural analysis program. It's a trajectory program. That's the best way to describe it. It's to kind of see what's going to happen in your flight. Kevin says, thank you for the explanation. I'm glad that worked. We are over time again. Time flies when you're having fun, and I've had a lot of fun today with you. This has been great playing around. I like showing off the launch visualizer, and I encourage you to try it. You can sign up for a free account right now. We're still in beta, and the programmers assured me by the end of the month we're going to be out of beta. So by January 31st, we're going to stop the beta testing, stopping fixing the bugs, and we're going to go full on because it's running pretty good right now. There's those little bugs, nuisance bugs like the ones I showed you, where in the chart it was showing meters, but in the launch visualizer where you see the rocket going off, it wasn't the same units that the user chose, and those should be the same. So that's a nuisance bug. It's still working fine. So I am the issues that they're working on now is credit card payments, and they're doing a lot of multiple user testing. So basically they set up a system where they've got hundreds and even thousands of users all using the launch visualizer at the same time to see how it affects the speed of the visualizer. And so far the results have been phenomenal. The part where it runs the simulation in the background, that goes fast. Now the part where you're trying to drag the position of the rocket using the time slider, that's going a little bit slower because that process is actually done on your local computer and it's not done in the cloud. So that's why it's slower. And to make that faster, you just need a faster computer. That's really what it comes down to. And I can't control that. Like I said, there's one thing you can do is turn off the flame and the smoke. And so when you scrub through the time slider, it should be a little bit faster. And it will make your computer work less hard. And when you're orienting it around, there's a lot of math going on in the background. You know, this is high power, three-dimensional geometry math. And every time you slide, it's got a, you know, it's not here and here, it's every point in between as the camera is moving. And so if you want it nice and smooth, instead of jumpy, it's got to do a lot of work, a lot of calculations. This is high calculation math, kind of like rendering video type of calculations. So that's kind of why it moves a little bit slow, and I can't fix that part. But the rest of the software right now seems to be working really good. And so, you know, we're really close to releasing it out of beta. And once we're out of beta, then we'll start taking people's money. And if you make an account right now, what's going to happen is we're going to delete the account so that we can start with a brand new, fresh database, because the programmers have been loading it up with all kinds of junk. So we'll go with a clean database, and that will make things run even better. And then, so then basically you just redo a new account. And so that's going to take like 30 seconds. So just be prepared for that if you make an account. So right now you can you can use it for free. The free version, you're limited to up to a D motor. If you want to go up to a G motor, you got to make a free account. And the free account also allows you to upload files like I did with the level 2 rocket. I uploaded it into the cloud. And we need you to make an account so that we know where to store your data, because that's associated with you personally. So we're not trying to collect your email, we're just trying to reserve storage space for your designs so that you can control it. And then the part that you can't do right now is anything above a G motor, like an H motor and bigger. That is only for the beta testers. The beta testers have been using that feature, and they're loving it. They're doing some big stuff. So anyway, maybe a gray-haired, experienced rocketeer frowning icon for risky flights. in the, I see what he's saying, you know, where you get under your simulation results, he wants a frowny face saying something not safe here. Okay, so I gotta stop because we've gone way long and your time is important. So thank you for coming. We will be back next Friday at 2 p.m. and it will be Michelle running the show next week. I have to go out of town, so she will be here. She knows RockSim really well. She doesn't know everything, but she can answer most of the questions that you've been posing towards me. Particularly, you know, how-to questions, how to design rockets. That's her specialty. You know, things like the coefficient of drag that I kind of just explained today, what she would probably do is say, well, we'll leave that one for Tim the next week. And then in 2 weeks, I'll be back. So I should be here, no problem. So Deep Thought says, thanks, Tim, and goodbye. And so I'm going to say goodbye and stay safe. COVID's going around. But by next week, I should be 100% better. I don't think I have COVID. I just think I just have a little cold. It's just right now, I've been talking a lot today, so my voice is going. So we'll see you again in 2 weeks, but be sure to be here for Michelle, because that's, you know, it's Michelle. So I'm going to end the stream in 5, 4, 3, 2, 1. Go out and launch something.